So let's look at the other example. Here I have a RL circuit. I have R is equal 100 ohms and L is equal 100 microhenry. And in this case, I would like to find the transfer function, and also I will determine the cutoff frequency and the Tmax, the passband gain, and sketch the Bode plots using the straight lines. So these are things similar to the last example. In this case, TV is going to be based on the Bode division. And that's going to be equal LS over LS plus R. So if I write in the form of 1 plus S over something, so in that case, I'm going to divide the numerator and denominator by R. So I get a L. So in this case, L over R divided by 1 plus S L over R times S. So in this case, I'm going to divide this by so I can do S over R over L and 1 plus S over R over L. So R over L is, remember what's R over L? R over L is 1 over the constant, time constant. We know the time constant for the RL circuit is L over R. So therefore R over L is equal to 1 over tau. So in this case, R over R is 100 and L is 100 micro. So in this case, we got 10 to the power 6. So 1 over tau is 10 to the power 6. That means the time constant really short, is 1 microsecond, right? So in this case, we're gonna have R over L. Yeah, so we're gonna have the circuit in this form, the transfer function in this form. So that's gonna be equal S over 10 to the power 6 and 1 plus S over 10 to the power 6. So in this case, we have two terms, right? The numerator represents a straight line that across this omega c. So in this case, and this will have a straight line, and the denominator term, or 1 over the denominator term, represents a low pass filter that has straight line until to the point of omega c, which is 1 meg radian per second, and then decrease at negative 20 dB per decade slope. And if we add these two, we will have this high pass filter, right? So this represents our high pass. And we're gonna look at the omega c is just equal to 1 to the 10 to the power 6, 1 megaradian per second. And the Tmax, so at high frequency, so let's see S equal to infinity. So in this case, let's say Tj infinity. If we take the dB, what do we get? So in that case, the denominator will be dominated by S over 10 to the power 6 term, and therefore this is going to be equal to 1. So that's equal log 1. So we got a 0 dB. So if we sketch this Bode plot, so the gain plot here, we have the gain plot as we did multiple times. So in this case, I don't really need that much negative, the positive part, because the 0 dB line is the maximum, so the Tmax, so this is equal to Tmax. And so this is Tj omega dB, and the horizontal axis is omega. So in this case, I have 1 meg, and I have a 10 meg, I have 100k radian per second, right? So let me using the change of color. So in this case, at a high frequency, this is going to be a straight line, right? At low frequency, there's going to be a 20 dB per decade slope, positive slope. So in this case, if I label this, I will label at and here I got a negative 20 dB, right? Negative 20 dB, and here this is 0 dB. So in this case, every 10 time frequency or 1 decade, I have 20 dB change. And for the phase plot, so in that case, the phase plot would be in this case, let's see, we have this 3 decades at high frequency. What the angle, and a high frequency, the angle is 0, right? Because at a high frequency, the numerator has 90 degrees, and the denominator also has 90 degrees. So we have a 0 at a high frequency. I'm using the black color again. At low frequency, we have a 90 degrees. And so in this case, I have high frequency. I have 0, and I have a 90 degrees. So this is my gain plot. So I have a 90. So this is theta omega, so this is 90 degrees, and this is 0. And here we got a 45 degrees. So in this case, the theta omega infinity in this case is equal to 0 degrees, right? So that's the approximation. And let's see, I also had a exact plot for this example as well in the Google Colab notes, and this is the actual plot. Okay, so the exact plot. There are no approximation here. So we observe at the corner frequency is 1 mega radian per second, and at low frequency we have 20 dB per decade, slope positive 1, right? And we go flat at 0 dB line after this corner frequency. For the phase plot, we have 90 degrees at below the 10 times below the corner frequency, or 100 k radian per second, and then above 10 mega radian per second, we have very close to 0. So that's our approximation. In the transition frequency range of 2 decades, we have a negative 45 degrees per decade. Right? That's for this example. So next, I'm going to show you on the op-amp circuit that's on the breadboard here.